it too for record keeping purposes. And
okay, so I'm going to start now.
Okay.
Okay.
Go ahead.
Okay. All right. Well, thank you very much for letting me present the ANI experiment in a plenary session. So first of all, I'll give you a small overview of ANI. This is a recent picture of the collaboration taken a few days ago. ANI is the Accelerator Neutrino-Neutron Interaction Experiment. It is a gadolinium-loaded water Cherenkov detector that is placed downstream of the booster neutrino beam at Fermilab. The primary goal of ANI is to measure the production rate of neutrons from neutrino interaction in water as a function of muon kinematics. I should change this. It's also a demonstration of new technologies in the field of fast photosensors and detection media. So ANI finished taking background data, what we call phase 1, and is soon to be taking physics data, what we call phase 2, that is now funded and under construction at Fermilab. So first of all, I'm going to explain a little about the motivations behind ANI. And as I said, so one of the motivation is the study of the multiplicity of final state neutrons from the nucleus interaction in water. This is interesting for long-base association physics because the presence of final state neutron after an interaction are a sign of inelasticity in charge current interaction. So understanding this neutron yield is actually very crucial when it comes to reconstructing an event and reduce any kind of bias you could have in neutrino energy reconstruction. And this also could allow a statistical separation of neutrino and antineutrino in a beam. And the second purpose for this motivation is the neutron tagging. So neutron tagging, as you heard before in the previous talk in this conference, is a critical signal to background separation tool. Proton decay searches, as well as the detection of the diffuse supernova neutrino background, rely on a very good understanding of those neutron yield in atmospheric neutrino interaction, because those are background for those interactions. So both of those searches are actually a focus of the supercamera Conde experiment loaded with gadolinium. And ANI will actually provide a high statistic measurement of this neutron yield in the energy range of interest for supercamera Conde that they could actually use to improve their dataset. The second goal is the technological goal. It concerns fast photosensors and novel detection media. So concerning fast photosensors, we plan on installing in ANI what's called LAPPD, or large area picosecond photodetectors. As you heard from Alexei Dyashenko yesterday, 2 days ago, those are 20 by 20 centimeter plates, microfinal plates with a very good time resolution of 60 picoseconds and a very good spatial resolution of less than a centimeter. ANI will be the first experiment to actually use this new technology in a running experiment and to take data with it. And those will be combined with also new fast deep buffer electronics. So after ANI is done running, this will demonstrate that LAPPDs are actually ready to be commercialized as actual photosensors for high energy physics, the same as photomultiplier tubes. And concerning the novel detection media, so ANI is also the first application of gadolinium-loaded water on a neutrino beam above ground. But we also plan on using this novel detection medium called water-based liquid scintillator, or WBLS. That's a mixture of water and liquid scintillator to allow the emission of both Cherenkov light and scintillation light. So the final word on the motivation, ANI will allow the combined use of all those technologies I presented in a single high statistics experiment. So now I'm going to present you what is ANI in more details. So first of all, the ANI collaboration. This is a somewhat older picture of the collaboration with our very first LAPPD in the center. ANI is a collaboration between 3 countries, the United States, the United Kingdom, and Germany. This is the location of ANI on the booster neutrino beam. So this is an aerial view of Fermilab. You can see the booster neutrino beam here. ANI is located 100 meters away from the booster neutrino target. It's located here. So you can see that this is the honey hole and neutrinos are coming from the bottom left. But if you actually have been to Fermilab in the past months, you will notice that this is actually not the honey hole. This is the honey hole. This is the very smaller building next to the SBND hall. And the ANI detector is actually located 2 stories underground in this particular smaller building. So the ANI detector, so as I said, it was installed in the Cyben hall on the BNB line. This is a gadolinium-loaded water volume of about 30 tons. So this is the first sub-detector, the water volume. It's instrumented with about 130 photomultiplier tubes of different sizes and at least 5 LAPPDs distributed in the tank. Two of the other sub-volumes are the front veto, you can see here. Those are scintillator paddles that are, the purpose of those paddles is to actually tag charged particles that would originate from the rock, to actually make sure that any kind of interaction you see actually originates from the water and not the rock. And the muon range detector, or MRD, this is a legacy from Sibun. It's a steel scintillator sandwich detector that is capable of reconstructing the muon direction and their energy after a neutron interaction. And I will finish by giving you an expected event rate. So any expect to see about 10,000 charge current interaction per ton in nominal beam running of 2, 10 to 20 proton targets. So how will Annie actually work and detect neutrinos? So first of all, you start with charge current interaction in your fiduciary volume here. This interaction will create a muon that's going to travel in your water and in your MRD. You will reconstruct the momentum and the interaction vertex using the FEPDs placed downstream of the beam. And the momentum, the rest of the momentum will also be reconstructed in the MRD. And then when your event happens, you may create neutrons. Those neutrons will channelize in the water volume to be subsequently detected and captured on gadolinium atoms that will release about 8 MeV in a gamma cascade. And this gamma cascade will actually see it with the numerous PMTs that we have in the water volume. So I mentioned the FEPD a lot, but why does Annie actually need the FEPD? Well, first of all, you actually need to use a very well-known neutrino beam, as well as you need to be able to reconstruct muon kinematics and understand the interaction to actually provide a useful result for the study. And the FEPD drastically improve our vertex resolution, our angular resolution, and the momentum transfer resolution. So where would you need to improve your vertex resolution? Well, first of all, that means that you can actually better reconstruct your interaction point, and you can better understand your neutron containment in the Annie volume that is actually quite small compared to other experiments. And this is a simulation that was performed by Annie collaborators with different photo coverage. The first one with only 130 PMTs, and the other one with the same number of PMTs plus 5 FEPDs. And you can see that this is a cumulative plot of the vertex resolution. The improvement is pretty drastic. You go from 40 centimeter to 12 centimeter vertex resolution, which is crucial when you deal with a 3 cubic meter fiduciary volume. You actually also need to understand your muon kinematics a lot better, since you want to better reconstruct the neutrino energy. And finally, the position resolution of the LAPPDs will allow you to detect multi-tracks events. That is actually also very important in a small detector volume such as Annie, when your tracks don't have a lot of time to actually spread, a lot of distance to spread. All right. So first of all, now I'm going to describe the first phase of Annie. But before, so Annie was actually designed to be a multi-phase experiment, with phase 1 being the engineering run and the background measurement run, phase 2 being the actual first physics run, and possible phase 3 being also a physics run, but also a test bed for new technology. So let me focus for a little while on phase 1. So as I said, phase 1 was the background measurement. We wanted to measure the beam-induced neutron background to make sure that phase 2 was feasible. So you have two sources of different beam-induced neutron background. The first one are the skyshine neutrons, so neutrons created in your beam dump and in your beam horn that would be scattered in the atmosphere and then rain down on the detector, so mostly coming from the top of the detector. And the second one are dirt neutrons. That are actually neutrons originating from neutron interaction in the rock. So surrounding your detector, you have this huge amount of rock. Neutron interaction would happen in them, create neutrons, and you would see those neutrons, but not the actual interaction. So we did phase 1. So you can see here some pictures of the assembly of phase 1 and data taking. We moved neutron sensitive volume in the vertical and horizontal axis to make sure that the neutron background was low enough in the fiduciary volume, and it is. We measured the neutron background per sphere to be less than 2%, which means that with this neutron background, this is not an issue for phase 2 physics, and phase 2 can actually start taking data. But what's also very important for phase 1 is that phase 1 actually relied on all of the key physical infrastructure that we're going to use for phase 2. So that allowed us to besides just saying that the neutron background is low enough, that allowed us to gain the experience to actually better design our physics run. And speaking of the physics run, we are moving now towards a fully operational detector for Annie during the phase 2. So a new inner structure to hold additional photomultiplier tubes. We're going to load gallium sulfate in the NE water. We're going to, of course, deploy LAPPDs and the fast electronics that goes with it to read the signals. And we're looking also at a fully refurbished MRD. So ANI phase 2 is now fully funded and under construction at Fermilab. Most of the photomultiplier tubes we have ready on site and ready to be tested and installed. We now fully refurbished the MRD. All the high voltage and electronics racks are ready to be populated. And the infrastructure to hold all of those detectors, PMTs and LAPPDs, is now being welded and mounted, and we can load photomultiplier tubes on it in the next future. All right. So about ANI, the relationship between ANI and LAPPDs, you have to know that ANI has been an early LAPPD adopter since the beginning. As you can see on all the different design here over time, all of the ANI design actually include LAPPDs. ANI has strong ties with the income company, the current manufacturers of LAPPDs, as you can, and you probably learned that during Alexei's talk 2 days ago. So I want to also mention that LAPPDs are now a real thing. They are commercially available, and several buyers have been already identified and received some of the tiles. And one of these buyers is us from ANI. 2 of the first tiles, LAPPD tiles, to actually go in ANI have been received and have been thoroughly tested. So here are a few pictures of those tests. This is a dedicated LAPPD test stand with an LAPPD here. This is LAPPD 25, the first one we received, and a dedicated very fast picosecond laser. You can see some results from a test, including waveforms and the transient time spread, which is lower than 60 picosecond, as I said before. And those are pictures taken a few days ago of our second LAPPD before and after opening. And this LAPPD will also be tested very soon. So with those LAPPD, what can we do with ANI? So first of all, as I mentioned, one of the primary physics goals of ANI is the neutron yield as a function of lepton kinematics. The second one is actually the measurement of the charge current cross-section on oxygen to be also complementary with other measurements, other cross-section measurement performed on the BMB line on carbon and liquid argon. But as you can imagine, as more and more data is being collected and the detector is being upgraded with more LAPPDs, for example, a broader range of physics programs is actually available to us. For example, we would be looking at measurement of the charge current resonant band cross-section, as well as a possible measurement of the neutral current cross-section. But this also allows us to test and probe a wider range of experimental techniques, including energy reconstruction. There will be a kinematic and calorimetric energy reconstruction, detection of de-excitation gammas in water, and the possible Cherenkov scintillation light separation using water-based liquid scintillator and fast photosensors. So I want to finish on phase 1 by giving you a quick timeline of phase 1. So first of all, we plan on filling the detector with pure water in March 2019, so very soon. After this, we'll have a commissioning phase that will last until we actually load the detector with gadolinium and take data with this gadolinium-loaded water from April of next year until July in 2 years. So physics that they are taking, we actually will perform this neutron yield measurements and the charge current cross-section measurement with a possible charge current 0 pi measurement as well. And then as we add more LAPPDs in the tank, so I put as a timeline the fall of 2020, we will increase our sensitivity to perform a neutral current cross-section measurements. And then, as I will discuss in the next few slides, a possible phase 3 in 2020, and I think I made a mistake here, it's not the same time, where ANI will be a test bed for new technologies. And this is the last part of my talk, is what could we do beyond ANI phase 2? And I want to mention that this logo, that is not the official logo, actually predates any kind of, predates the actual design of the TIA experiment, which means that ANI was actually thinking of going bigger before TIA was even a thing. So I mentioned before water-based liquid scintillator. I think I have this 2 times. Okay, never mind. So water-based liquid scintillator in ANI would allow us to separate Cherenkov and scintillation light to actually make a combined kinematic with the Cherenkov light and calorimetric with the scintillation light measurements of the energy reconstruction. And for this, you would actually separate the 2 using both time and charge. As you can see here, this is a simulation in a much bigger detector of a CC event in water-based liquid scintillator. You can see the Cherenkov ring clearly here, as well as the entire detector being lit up by scintillation light. But to do so, especially in a detector such as ANI, that's much smaller than any kind of detector like TEA or Watchman, you actually need fast photosensors. And that's perfect for ANI since ANI is already loaded with LAPPDs. So the scintillating light also increases your neutron detection efficiency since it lowers the threshold of detecting charged particles. And speaking of charged particles, you would also be able to detect protons with such a low detection threshold that is brought up by the scintillating light. So this combination of water-based liquid scintillator with fast photosensors that is the main physics case for a possible ANI phase 3. And of course, as you can imagine, this would have also this would have crucial advantages for experiments like Watchman and TEA in the near future. And the goals of ANI. So the primary goal of studying the multiplicity of state neutron in the interaction in water. We also perform a measurement of the CC inclusive cross-section in water, as well as demonstrate the combined use of those new kind of detection media and fast flow sensors together. So ANI phase 1 was a success and demonstrated that ANI phase 2 is actually feasible with a very low neutron background. And speaking of ANI phase 1, we are currently writing a presentation to summarize all those measurements. As you saw, ANI is moving into phase 2 and will very soon take physics data, expected in the beginning of 2019. And we are also looking towards the future, looking at adding water-based liquid scintillator and more fast flow sensors for possible phase 3. And thank you for your attention. All right, that's 16 minutes-ish.
Yeah, about 16 and a half minutes.